Hello everyone, my name is Ibrahim from the National University of Ireland, Galway, and I'm presenting a research paper under the title of Investigating Natural Ventilation Behaviour of Passivhaus PHPP using CFD Building Simulations, on behalf of myself and Dr. Carlos Jimenez Pescas from the University of Nottingham. Describing energy efficiency as the first fuel, the International Energy Agency has stated that there is potential for significant benefits associated with energy efficiency. Energy-efficient measures, such as the implementation of natural ventilation, might have negative impacts on the indoor environment status if not implemented correctly, as it is a directly related factor to thermal comfort, indoor air quality, and overheating risks. Therefore, studies that implemented pre-design and early design stages tools that enhance the mechanism and operation of such measures are of great importance in terms of realizing better performing building. In terms of ventilation, whether forced or natural, CFD simulations implementations have dispensed a range of outcomes that have had crucial implications in this field. While assisting designers and modelers with decision-making, CFD have taken the simulations towards better design approaches of active and passive cooling behavior of airflow. Studies that implemented CFD in buildings design and investigations have varied in aims and objectives, whether individually or assisted by other pieces of software as a combination, for conventional and low-energy building concepts. Eventually, a range of studies have implemented CFD simulations and building energy modeling softwares in an attempt to lower and optimize energy use in all building concepts. While the Passivhaus design approach and certification depend on Passivhaus planning package PHPP steady-state building simulations, including the natural ventilation assessment, design, and planning, this paper aims to assess the effectiveness and behavior of Passivhaus ventilation plan taken from the Passivhaus planning package Natural Ventilation tab through the implementation of CFD simulations. The process of this study comprises two main phases. The first phase involves data extraction of the natural ventilation plan from the PHPP and applying it in the second phase through the ANSYS CFD software. The PHPP natural ventilation data is extracted from hygienic air exchange window ventilation strategy and the additional night ventilation strategy. The window group's quantity, openings, clear width, and clear height values are modeled in the ANSYS geometry step and translated to air velocity and exhausters through the air velocity inlets and air pressure outlets in the mesh step. In the ANSYS fluent step, air speeds chosen for the test were 0.5, 1, 1.5, and 2 meters per second, representing the usual air speeds that enter through windows in buildings from the annually average wind direction at the location of the Passivhaus building modeled in Chelmsford, England, and it was south-southwest. As for the outcomes of the simulations, apart from the main outcome, which is the airflow patterns and gradients of rooms area plans, the airspeed results were extracted for points distributed on the Passivhaus indoor areas on the mid-chest plane of height that happens to be 90 centimeters, simulating a sitting user's mid-chest level. On the other hand, two other parameters are extracted from the fluent surface integral reports, which are the uniformity index that describes how uniform the airflow is distributed on the covered area, calculated from 0 to 100%, and having the optimum values as from 75% and above. The second parameter is the area-weighted average airspeed, which is an average airspeed value for the whole area covered by the airflow. Relatively, the process takes the ASHRAE 55 rule of thumb as a reference of comfortable airspeeds, which takes the airspeeds above 2 meters per second as uncomfortable for occupants. Apart from the airflow patterns, airspeeds ranges at specific points, area weighting averages, and uniformity index values were extracted from the simulation results for each of the tested airspeed, besides identifications of any turbulence that takes place at certain points. Airspeed ranges were recorded in the medium of 0.05 to 1.94 meters per second in general, with area-weighted average range of 0.19 to 0.87 meters per second. For the uniformity index, the range recorded was between 0.67 and 0.75. And for the turbulence, Turbulence is recorded at the northeast and northwest outlet spaces junctions where the airspeeds above 2 meters per second have taken place, with both stories having air velocity ranges of almost 0 to above 3 meters per second. The lower higher airspeeds have not necessarily participated in producing a larger uniformity index in many locations. The results concluded the relation between airflow behavior and uniformity index, as higher speeds at certain points cause both higher and lower uniformity index values. In the 1 meter per second simulations, the rooms with inlets recorded a range of 0.6 to 1.2 meter per second, which has clearly no turbulence, staying in the comfort range. However, the simulations of the rooms with outlets windows have recorded uncomfortable airspeeds in certain locations, acting as the peak spots of the airstream. Yet, these results occurred when all the doors between the rooms are opened. As the figures show, airspeeds were doubled at most of the points, pushing the numbers closer towards the green range as optimum indoor air velocity sets. On a notable event, the uniformity index of the ground floor has recorded a lower value and a triple increase in area-weighted average air velocities in some occasions. And the same effect has taken place on the first floor as well, but with a slightly lower value, with both the uniformity index and the area-weighted average. Although the airspeed is only one of the factors affecting the uniformity index, as the windows, openings, and airstream controlling are another important factors. Another point is that the different airspeeds might produce the same uniformity index values across the same spaces, whilst the area-weighted average might even triple. And in the comparison between 0.5 and 1.5 meter per second airspeed simulations, we see this clearly. An important result to discuss is the uniformity index and the area-weighted average correlation. The chart describes the level of interconnection between the two parameters, showing how the high and low airspeed affect the uniformity index levels. Certain inlet airspeeds have produced higher uniformity index values, meaning more air distribution in the indoor space. And these speeds weren't necessarily higher or lower than each other. The higher or lower airspeeds did not necessarily lead to higher uniformity index values. However, other factors like room shape and airstream direction plan are important as well. And this is when the integration between the study process and the designer's approach come together. The variety of the results has provided the aimed-at description of the PHPP natural ventilation strategy in a comprehensive way through the CFD simulations. The process has the potential to aid designers through their early design stages and help them manipulate the passive cooling strategies at the most important indoor location for the occupant's comfort realization. The parameters of airspeed has come out as shown in a detailed description, allowing the natural ventilation strategy investigators and researchers to go in detail through further studies such as thermal comfort studies with its varied models, especially the PMV-PPD model. The different parameters produced have explained how they worked together, providing an image of the behavior of the relations and helping to reach a balance with a trade-off perspective in a parametric way or parametric method. Further applications are realizable where the approach could provide outcomes of passive cooling in terms of flexibility, alternative mechanisms, and courses of action. Talking about the limitations of application, they could exist, to be honest, in regard to specific building concepts that may rely on specific pieces of software for verification. At that, limitations could be also subjected to the indoor physical environment change and also practically in the perspective of multidisciplinary approach. That would be it, everyone. Thank you for listening.